Hello and welcome to my session on Grafana Cloud Graphite. Today is going to be a good day because I have some exciting news from the graphite side of Grafana Labs. If you're wondering who I am, well, I am Dieter. I actually was the first engineer to join Grafana Labs right after it was founded. So in this picture, you can actually see Raj, Torkel, and myself discussing our first product, which was our first version of WorldPing, more than 5 years ago. But the vast majority of my time at Grafana Labs, I've spent building and working on our Grafana Cloud Graphite platform. But I think this story is better told through some GitHub commit charts. So you can see here on the left column that I was already quite involved with the Graphite project and especially its ecosystem, even several years before Grafana Labs even got started. And that's actually one of the reasons why I ended up joining this company. In particular, Carbon-relay-NG used to be a hobby project of mine, but then Grafana Labs decided to pick it up. And that means I've kept maintaining it ever since. And we use it now as our agent for Grafana Cloud Graphite. As you can see on the Grafana panel, I've only done a very few amount of commits. In the early days of the company, I worked a little bit on Grafana's backend, specifically around the alerting. Then I didn't work on Grafana itself at all for years. And now more recently, I worked on some integrations between Grafana and Grafana Cloud Graphite, which I'm very excited about, and I'm going to demo those later. But it's pretty obvious probably on this chart, if you look at this Metrictank chart, that I've spent the vast majority of my time at this company working on the Metrictank open source project, which is the backbone of the Grafana Cloud Graphite platform. So the agenda for today, we're going to start with some news around the Graphite and Carbon-relay-NG open source projects. And then the majority of the presentation, I'm gonna do a deep dive into some new features on Grafana Cloud Graphite. The first one is meta tags. And meta tags is a feature that enables you to ad hoc add tags to your existing metrics, which makes it much more flexible to do more powerful analysis on your data. And then we're going to look at response metadata. There's two kinds of response metadata. There's the performance stats, which tells you about your query performance and which lets you optimize your queries. And then there's also the lineage information, which tells you for the series that are returned, which rollup did these series come from, were they runtime consolidated, and so on. This is sometimes a source of confusion for people, and this metadata really helps with understanding what your queries are doing and helps you improve them. And then finally, we'll have some project updates from the Metrictank project. So let's start with Graphite. In the last 6 months or so, there have been 2 Graphite releases. So I just looked through them and handpicked a couple of interesting news updates that I wanted to share with you. The first one is a new write strategy for Carbon. So if you're using Graphite with Whisper, then you might be familiar with this write strategy, which is kind of like an IO scheduler in the sense that it tries to balance which write operations to execute and how to schedule them, how to time them, and to reduce your IOPS and trade them off against CPU and memory usage. So a pretty common approach to do this is the max write strategy, which whenever you issue a write to Whisper, it will look at which series has the most amount of points pending, and then it will flush that one. It's a pretty sensible approach. The bucket max strategy is an improvement on this. It does the same thing, but it achieves it by having a more optimized data structure where all the pending series are keyed by the amount of points that they have pending. So this makes it faster at every write to immediately find the right series to look up as opposed to having to go look for them. And Piotr, the author of this change, he shared this screenshot with us. So you can see on the first run, which uses the new bucket max strategy, then the middle run uses the older max strategy, and then the third run uses bucket max again. I think you can see pretty clearly that bucket max uses less CPU. So give this a try if you're using Whisper. Then, on our platform, we see that customers sometimes send strange or interesting queries, shall we say. And my colleague Mauro has actually done a lot of work in handling these queries better. He's filed several PRs. I actually couldn't fit them all on my screen. But basically, one thing we would see is when people specify invalid arguments in their queries, those would previously lead to internal server errors in Graphite. And as a client, you would get this response back that has like a stack trace, or it has HTML code and has a status code of 500 saying internal server error. We cleaned all that up. We added validation. So now we give you much clearer error messages that say, this is what's wrong with your query. This parameter is wrong. And of course, now we have correct status code of bad client requests, if that's the case. And then the other thing is sometimes people would pass values that are kind of right, but not really. Like, for example, instead of an integer 5, they would specify a floating point like 5.0, or they would put quotes around it, then it becomes a string. Or instead of booleans, they would pass strings. So we've tried to stay as backwards compatible as we can, and we actually achieved that. And we accept those when we can figure out what the user actually wanted. But we do a much better job now at validating the queries and doing something sensible with them. So once we have that validation in place, not only do we return better errors to users, we also log these errors, and now you get much more useful log messages with your query errors. And this led to the next question, which is, well, okay, I know that I have a bad query, but where did it come from? So we also added more information to these log messages, including the Grafana dashboard ID, the Grafana panel ID, the organization ID, and so on, which makes it much easier to go from your query log and go back and fix the problem right where it is on a specific Grafana panel on a specific dashboard. Now, I should probably also mention at this point that if you're a Grafana Enterprise user, it actually comes with an Insights feature where it knows which dashboards and panels generate errors, and then it will let you dig into those straight from the Grafana UI itself. So that might be interesting to you. So now let's look at Carbon-relay-NG. There was a release end of September last year, and we're also working on the next release, which we hope to release in a couple of weeks. And again, I've selected a couple of interesting changes that either have been released already or will be very shortly. The first one is that now the relay emits its own stats about its own memory usage and its CPU usage, as well as Go garbage collection information. This has proven quite useful already to track down issues, because sometimes, for example, if you have a lot of aggregators or a lot of route matching, you may be doing a lot of regular expression matching that increases your CPU, and in this way you can easily just see what the problem is. And actually it makes it easier because there's a lot of people who just run a small VM with just a relay on it, and now you don't have to deploy an agent anymore. If all you want to do is just monitor the relay-NG itself and there's nothing else going on the host, now you don't have to deploy collect-D or Diamond, because you get the most important stats from the relay itself. Then before I talk about the next feature, I have to remind you that if you're a Grafana Cloud user, then you already get this dashboard where you can see your active series, you can see your ingestion rate, and you also get a panel that shows you which metrics we have to drop. For example, if they have an invalid format, or they're out of order, or tags are not specified correctly, or anything like that, we have to reject those incoming points. And we expose this on the dashboard, and it's a regular query, so you can set alerts on it if you want. But that brings us to the next question, which is, sometimes users would say, okay, well, I'm sending bad data, it's getting dropped, but what bad data? Can you please show me an example? And this is what this next feature of the relay solves. So as you can see here on this very trivial example, we're submitting 3 metrics. The second of them has a problem in the first tag. It's not specified correctly. So what we do now on our side, we look at all the incoming data, we validate everything, and then we feed that information back to the client. And we say, okay, this is an error that we've seen, and here's some examples of metrics that cause this error. It could be multiple errors, and you may have many metrics that were problematic, but we also give you a subset just so that you have some examples. And this response here, it basically shows that in action. It says 1 invalid metric was dropped, 2 of them were published, and the error was invalid tag format. And here's an example. There's a couple more interesting features for Carbon-relay-NG that I can't dedicate too much time to, but I just wanted to give a quick shout out. The first one is pprof endpoint. So if you want to do any profiling on the relay to get a deeper understanding of why it's using a lot of CPU or memory, then that's now much easier. If you run Carbon-relay-NG in a secure environment, then the second entry here will be quite useful to you. So historically, the web UI of Carbon-relay-NG would pull in these resources from the internet. It would pull in Bootstrap and CSS files and all that. But now everything is compiled into the binary itself. So when you use the web UI, it can serve everything up itself without having to connect to the internet, which is obviously much more secure. It's now also compatible with all the versions of Pickle and all the different ways that you could deploy a Pickle-based setup. So now you can have, for example, a traditional Python Carbon-relay and Carbon-relay-NG behind it, or you can first have your Carbon-relay-NG talking to the Python Carbon-relay and everything speaking Pickle to each other, and now all of that works very well. And then finally, the Grafana Cloud configuration can now be set as environment variables, so you don't have to do it through the file if you don't want to. So now let's look at Metrictank or Grafana Cloud Graphite. Grafana Cloud Graphite is the platform, Metrictank is the open source project. It's pretty much the same thing. At least all these features I'm going to show work on both. And the first feature I want to talk about is meta tags. Meta tags is a major feature that we've been working on for a very long time. As you can see, the design doc came out in September 2018. We worked on this all throughout 2019, and earlier this year, it basically became GA, which is very exciting because now you can use it on our platform. So what is the problem that meta tags try to solve? So first of all, we want flexible assignment of tags. You want to be able, or at least many people want to be able to add tags to existing metrics without having to change anything upstream. They don't want to change their agents, or they don't want to change all the existing code that they already have live. They just want to say, all this data is coming through. Now we just want to add additional tags, and it should just work. The next thing is that reassignment should also be flexible. You should be able to change values of tags without changing the time series. So normally when you have a tag defined on a metric, whenever you change the value of that tag, that will actually become a new metric and a new time series. But sometimes you have this information that's kind of more extrinsic or external to the metric, just additional metadata that you want to apply and that you want to change over time, without really changing the metric itself, without creating new time series. And that's also what meta tags solve. And then finally, resource usage was also quite important for people who run very large deployments, because these kinds of metadata tags could be, like Linux version, operating system version, and so on. A lot of these values are repeated across many metrics. So you may have tens of millions of metrics or hundreds of millions of metrics. And you don't want every single metric to always repeat all those same tag names and tag values over and over again in every single metric. Instead, what we want to do is we want to have one central place where we define some kind of associations that then affect those metrics, which basically means much less memory used. So how do we achieve this? As I mentioned, it's through associations. So basically you have a tag query that matches against your data set, against your existing metrics, or also new metrics if they come in. And you basically specify which tags to apply, which meta tags to apply. So you say, these meta tags I want to define on all the metrics that either already exist or come in the future that match a certain expression. And it's really important to point out that these look and feel just like regular tags. I'm going to show this in the demo in a minute, but it's important to know that as far as filtering goes, aggregations, querying, all of that, as you're using it through Grafana or through queries, they look and feel just like regular tags. So let me show you the demo. For this demo, I have prepared some example data. So I created some metrics that represent latency of a web application that runs on various hosts. So let's just imagine that we received an alert that the latency of our web application breached the alert thresholds. So step one is, of course, looking at this data. Now, it is tagged data, so we can look it up by any tag. Typically, we use the name tag to look up a metric by name, as I'm doing here. So we can see that some of the latency metrics went up, whereas others remain the same. We can also see that the series have several tags, such as the host name, the zone the host is in, as well as an application version tag. And we also have many host values, as well as different zones and application versions. But it's unclear at this point which tag values may correlate to the problem. So a common troubleshooting approach is to simply look at aggregations across each tag and find a tag that shows a correlation with the problem. So let's try the tags one by one. Let's start with zone. What I'm doing here is asking for averages segmented by the zone tag. In other words, all the metrics that have the same zone value get aggregated together. This way we can draw conclusions on a per zone level. We can see that when we average by zone, there is no clear correlation. Both zone values exhibit the same latency spike. So let's break it down by another tag. Let's look at different hosts. As we can see, there's many hosts, some of which exhibit the problem, whereas some of them don't. This also doesn't really help to narrow it down, so let's look at our final tag, the application version tag. This one seems interesting. There's somewhat of a correlation. It looks like version 1.1 of our app is much more affected than 1.0, but 1.0 also saw an increase. So what we're seeing here is likely just coincidence or not really related. If you have experienced troubleshooting incidents, this situation will probably feel familiar. Our metrics are broken down by various tags. Some of them give us clues, but none of them fit the bill exactly. Not a single tag is telling us what the problem is. This can be quite frustrating, and what we really need is more ways to break down the data. We want more dimensionality on the data so we can analyze better. And that is exactly what meta tags provide. So let me just switch to my terminal. The administration of meta tags happens through the REST API of Grafana Cloud Graphite or Metrictank, if that's what you use. They expose the same API, of course. So first, let's confirm, and we can see there aren't any meta tag rules yet, which makes sense because we didn't add any. So let's add some. This is the file that we're going to use. As you can see here, meta tags are additional tags that we can add to our metrics through associations. They provide a cheap way to enrich our metrics with all kinds of useful metadata. Note that these expressions are regular tag queries, and on the results of these queries, we will apply these additional tags. So depending on the host names in this example, we classify the hosts with hardware vendor information using the server tag. And similarly, we can also tag all hosts with the version of Linux that they are running. Anytime you upgrade your Linux version, you would update the rules and simply submit them again and they will take effect immediately. Note that even though all our rules match on the host tags in their expressions, you can match on any tag you like, including the name of the metric. You can specify tag queries as simple or as advanced as you like. So let's execute this. We post this to the meta tags swap endpoint, and this will replace the current set of meta records, which is empty as we saw, with the new ones that we're posting. So now that they're posted, we can go back to Grafana and aggregate on these new tags. When we aggregate by server, similar to before, nothing stands out. So let's check the Linux version tag. Aha, now this is interesting. We can see there is a perfect correlation. Who would have known? Some machines were upgraded to Linux 5.6, and that seems to be our culprit. Thanks to the additional meta tags that enrich our data, we could drill down more and find what the problem is. Now it would be nice to know which hosts exactly are the offending ones, so let's query for them. Now mind you, meta tags look and feel just like regular tags, so we can simply add a clause for Linux version 5.6 and we will get our hosts back. And yeah, so we just switch to version 5.6 here. And now let's just alias these series to just those host values to make it a little clearer. Okay, and now we found our offending hosts. To double check, let's just invert the Linux version condition real quick. Indeed, when we look at all the ones that are not 5.6, none of these hosts exhibits the problem. And when we switch it back, we know exactly which hosts are the bad ones. There's more that you can do with meta tags that we didn't go into, but this covers the basic principle. Namely, you can add large amounts of additional metadata tags on your metrics cheaply and without having to change anything about the data being sent. You can use them for all kinds of information about hardware, platform, operating system, and really any additional metadata you like. You can then use these additional tags for querying and aggregation, just like real tags. And that can be quite valuable to get more insights about your data or find causes of issues much faster. Meta tags are really useful for additional properties, especially when they need to receive updates over time, such as operating system version and so on. The next feature I want to talk about is response metadata, and specifically the performance stats that are part of that metadata. This is really helpful in helping you optimize your queries. Let me show you how this works in a demo. Now, before I can show you the performance metadata, we have to double check our data source configuration. As you can see, I have two different Graphite data sources here, a Grafana Cloud Graphite instance and the local Metrictank. It doesn't really matter which one I use because they both look and feel the same. So for this demo, I'm going to use Grafana Cloud Graphite, and for the next demo, I'll use the local Metrictank. So whether your data source is Grafana Cloud Graphite or a local Metrictank, either way, it is a Graphite data source, but you should scroll down and double check that it is set to the latest version of Graphite and has type set to Metrictank. That is what will enable the metadata, so this is very important. Oh, and you need Grafana 7, of course. All this metadata functionality requires the latest Grafana. Now, let's go to the dashboard. To demonstrate these performance stats, I have prepared a query. As you can see, we have here a sum query that sums data across two different agents, and each has 500 series. So we are summing a total 1,000 series together. We see this scenario quite often where people do averages or sums across many series. This requires the backend to load many series and can sometimes be slow, even though the result is just a single series, as I'm showing here. So now we have this new feature where you can hit inspect to go to the panel inspector It doesn't really matter which option you choose here, as they all go to the same place, but go to the tab Stats. Once you go to the Stats tab, you'll get to see a bunch of interesting performance stats. The first 4 are stats from Grafana itself, where it measures how many queries it triggered, how long it took to process the response, and so on. And under this, these are the Metrictank specific stats. Resolve series is about how long it took to query the index. Get targets tells us how much time it took to fetch the actual data from the backend. Prepare series is an internal step. I wouldn't worry about this one. If it is ever a large value, send me an email and I'll be quite surprised. And then we have plan run. This is all the processing that was requested. You know, your sum series, your group by node, your summarize, and so on. This covers all the functions that you specify in your query. And then it tells us that it fetched 1,000 series and a total amount of points fetched of 900,000. This is simply because we requested 15 minutes worth of secondly points from each series, and that's 900 points per series. So we return 900 points because we only return a single series. And then we also get some internal stats about cache hits and misses and how many chunks came from the in-memory buffer, the in-memory cache, or the cold storage. And as you can see, we had to load a bunch of data that could not come from the cache. So it's no surprise that we spent most of our time fetching data. In this trivial example, it's not so bad, but some customers have heavy workloads and have queries similar to this that can take multiple seconds. So if you want to make a query like this faster, there's an easy trick, which is to create an aggregator in Carbon-relay-NG. So let me just show you how that works. In the Carbon-relay-NG config file, you can see here a very simple aggregator definition. It simply matches all the series that we were summing, and it generates a single total series using the sum aggregator. The output series will have an interval of 1 second, just like the input series do. And note that it will wait 10 seconds for any late data to come in before it considers an aggregate point to be done. I'll show you in a bit why this matters. So to activate this, you would normally restart your relay now, but I have already been running this configuration for a while, so we can immediately use it. Now let's go back to Grafana. Now we can simply query our aggregated series coming from the relay. Note that the aggregate series lags a little bit behind. This is due to that 10-second wait that we configured, where the aggregator makes sure that it has all the data before it generates the aggregate points. You can actually see that the original sum series sometimes seems to go down at the most current point, precisely because not all the data may have come in yet. So you can tweak that wait value to get a more robust value if you have slow senders, for example. So let's turn off the original sum series query. Our new query should perform much better. So let's look at the performance stats again. We can see that get targets and the time taken to load the data is much less than before. And the reason for this is, of course, that we now have to fetch only a single series instead of 1,000, and only 900 points instead of 900,000, because they all have been pre-computed. So one more thing, it's also common to issue a group by node query instead. This is similar to the metatext demo from earlier. What this query does is it will get the sums of all all series for the same agent value. So the sums for all of agent 0 and for all of agent 1 as a separate output series instead of a single total sum. And if we look at the stats again, we can see that just like before, we need the same 1,000 input series and we spend most of our time just fetching data. And we can also improve this with an aggregator similar to before. Now, the difference with before is that now we create a match group around the agent part, and we use that in the format of the output aggregate metric. This means that the relay will generate aggregates segregated by the agent name. As you can see, all the other parameters are the same. So in Grafana, we can replace our query again and replace it with an aggregate one. And of course, the data looks the same, but let's check out the stats. Now we can see that we only need to fetch two series, 1,800 points in total, and that the get target step is much faster than before. So this performance metadata tends to be really valuable to find why queries are slow. Perhaps you're requesting too much data, but it could also be expensive processing functions, slow index lookups, or anything like that. If you're requesting aggregates across many series, you can always speed up these queries by generating the aggregates in advance, like I did here. And I think a lot of these values in the performance stats help you show where you can optimize your queries. The next kind of response metadata is lineage metadata. Before I explain all this, let's make sure that we agree on what consolidation is. So a series consolidation is performed when you take multiple successive points of a series and you reduce them to single points using a certain mathematical function. So on this example, we have a series that has a point every 10 seconds, and we want to reduce that so that it has a point every 30 seconds. We do that by taking groups of 3 points together and taking, in this case, we take the average of those 3, but it could also be the sum of the 3 or the minimum value amongst the 3, the maximum, and so on. The next thing that I have to explain you is how the response path looks like of Grafana Cloud Graphite. So when you issue a query for data, the first thing that happens, of course, is actually fetching that data, that chunk data. And that could be either from raw data or it could be rolled up data. So roll-ups are a good technique that basically are consolidated storage on disk. So instead of using raw 10-second points, you may have minutely points or hourly points. Then that's how you store them on your long-term storage, which means you can store these for a very long time for much cheaper because they're lower resolution and they take less space. This is the same in graphite. Then after you fetch that data, it may need to be normalized. So what that is let's say you fetch one series that has 10-second points and then another series has a point every 30 seconds. And we need to combine those. So the way that works is we reduce the 10-second series to 30-second points, as I showed in the slide before this. And that way both series have 30-second points. And then you can take their sum, or you can do an aggregate across both series, or whatever you want to do. So this normalization only happens when you want to combine multiple series together. And there's two ways that this can be done. Either it can be done at runtime, as I just explained, or Metrictank also has an optimization called pre-normalization, where it would also take into account which rollups it has available. So that 10-second series, if it has a 30-second rollup available, for example, and it needs to combine it with another 30-second series, then it will just use that rollup data instead of normalizing at runtime. Then the third step is the function processing API. So all the functions that you requested, it could be your sum series, your group by node, alias functions, and so on. And the fourth step is runtime consolidation. So once your data has passed through all of these steps and it has passed through all your custom processing functions, then right before we return that data back to the client so you can plot it in your Grafana, we look at what is the max data points value. And typically Grafana will set this to the number of pixels you have available on your screen, because it doesn't make sense if you only have 800 pixels to return thousands of points, because you can't plot them all anyway. So after your data has come through the function processing, at that step, we may consolidate the series again and reduce the resolution to make the number of output points go under the max data points value. As you can see, there's various steps throughout this process where we may use data that has been consolidated, either because we read a rollup, or we had to normalize, or we have to runtime consolidate. There's a lot of opportunities here for consolidation, and sometimes this may lead to mistakes in queries, and the lineage functionality helps you understand what's happening and fix your queries. And I'm going to show you this with another demo. I told you there was going to be a lot of demos. So here we go. Just like in the previous demo, we have to make sure our data source is properly configured. For this demo, I'm going to use my local Metrictank, but again, it would be the same on Grafana Cloud Graphite. You need Grafana 7 and make sure that your data source is set to the latest version of Graphite and has type Metrictank. That is what will enable the lineage metadata. I would also recommend enabling this rollup indicator. It's a small handy indicator that will show up on panel titles. I'll show you in a second how it works. So I created some fake data that mimics website visits. Let me show you. I'm plotting 7 days here, and as you can see, this mimics a daily traffic trend like you tend to see on real website stats. This metric peaks at around 4,000. Let's zoom in on one of these peaks so we can understand better what data we're working with. As you can see here, there's 1 point every 10 seconds, and the value of these points is around 4,000. It's important to understand that in an account metric like this, each point contains the number of visits seen since the last point. So values of 4,000 means there were 4,000 visits in the last 10 seconds since the previous point was recorded. So typically, people want to visualize a metric like this by summarizing it into 1 hourly buckets or something like that. So let's do that. Now, if you have 4,000 visits each 10 seconds, then the number of visits per minute is 6 times that. So 4,000 times 6 is 24,000 per minute. And the number per hour is 60 times 24,000, which is 1.4 million visits per hour. This of course matches the peak shown here. It shows us that the hourly visits peak at 1.4 million each day. Now, let's look at where this tends to go wrong. Often people have a query that works fine, but then they start zooming out and look at larger time ranges, and then the data just looks wrong. Just like here. Our spikes now have values around 240,000. It looks like the scale of our chart is way off. The indicator already gives us a good clue. It tells us that we use rolled up data, and the data is aggregated using 1 minutely averages. But that's the problem. Because we use statsd counts, if we want a number of visits over 1 minute, it should be the sum of the 6 individual 10-secondly values, not the average, because the average would only describe a period of 10 seconds, and thus all our numbers are too low by a factor of 6. Like before, let's go to the panel inspector, and now we're going to use the metadata tab. This shows us the series lineage information. This menu tells us everything we need to know about how series were fetched and consolidated. First of all, it's telling us the name of the storage schema rule from the server configuration. Then it tells us which archive the data came from. We can see here we retain 10 seconds data for 8 days, 1 minute rollups for 60 days, and 30 minutely rollups for 1 year. These are the configured storage retentions. The green archive is the archive that this query read from. So we read 1 minutely rollups, and it also tells us it used the average function. Then it tells us it didn't need to normalize, which is logical because we didn't ask for a sum series aggregation across multiple series or anything like that, which is what would trigger normalization. It tells us it didn't need to perform runtime consolidation, which means the amount of points did not exceed the max data points value. And finally, it also tells us that 1 series was fetched using this profile. There's a lot of information here, but the main thing is now we know that our problem is that we read averaged rollups and we need to ask for summed rollups instead. And the way to do that is to add a consolidate by statement here and move it to before the processing. That way it applies to the fetch stage. Now we can see that our data is correct again. The peaks are 1.4 million, like they should be. By the way, this is a feature that Grafana Cloud has, but Graphite does not. With stock Graphite, you can only configure one rollup per metric, and you're stuck with it. But with Metrictank or Grafana Cloud Graphite, you can have multiple rollups per metric, and you can choose one at query time. And just to double check, the Lineage metadata confirms that we're now using some rollups, which fixes our problem. Now, let me show you something else. Let's zoom out a bit and decrease the max data points value to 50. This will trigger consolidation runtime consolidation, because we would have more points to display than the max data points of 50. The rollup indicator doesn't mention anything special because it only concerns itself with rollups. But once we look at the lineage metadata, it tells us that yes, this data has been runtime consolidated and it used the average function. So usually the desired runtime consolidation function has more to do with your particular use case or your information need and not so much correctness. So it's common for people to want to see their minimum rates or their maximum rates, which you can also do with the consolidate by function. And this part is actually the same as Graphite. So both in Metrictank and Graphite, you can choose your runtime consolidation with consolidate by, but it's specific to our platform to also use consolidate by to select a rollup to use, as I did earlier. And actually, I have another demo about this lineage metadata. This one, I want to show you how you can use it to improve on your normalization performance. For this demo, we can reuse the same series from the previous demo. As a reminder, this series has a point every 10 seconds. So let's just double check that this is correct. Now, whenever we do math across multiple series that have different intervals, that's when normalization happens. For example, let's add another series that we will sum later. Note that even though our original series had 10-second resolution, our new MyApp1 series has a point every 30 seconds. So think about what would happen when we want to sum these two together. We can only add them together if they have the same interval, and we can't increase the resolution of the 30-second series because we can't just make up new points. So instead, we have to reduce the resolution of the 10-second series. It must be converted to a 30-second series by consolidating groups of 3 points into one. Now, let's have a look at what the sum of these two looks like. Okay, so as you can tell, the resulting series is also 30 seconds. Of course, maybe pretty obvious. But let me disable the inputs so it only shows the sum. And then let's go back to the lineage metadata in the panel inspector. So this confirms our 10-second series needs to be normalized to be combined with the 30-second series. Our other series, the one that's native at 30 seconds, does not need to undergo any normalization, of course. But like in the previous example, it's normalizing using the average function. Because we're using a statsd count, if we want 30 seconds worth of visits, we have to sum up the individual 10-second counts. So we have to apply the same fix as before. We just have to add, again, the consolidate by sum. And now we can confirm that the series is properly normalized using the sum consolidator. But let's think a moment about this. We are fetching raw 10-second data, which is a nice amount of detail, only to then throw away a bunch of that detail as we turn it into 30-second points. Let's look at the stats. In total, we fetched 120 points to satisfy this request, but we only returned 30. Whenever you fetch many more points than what you return, that's usually a pretty good sign that maybe you're wasteful. Similar to the performance stats demo before, it's good to think about how you can reduce the amount of points fetched. Of course, this query is a very trivial example, but you can imagine that with real queries, this can be a lot more significant. I want to remind you that Metrictank has an optimization called pre-normalization. What this means is that when it will need to combine multiple series together and they have different intervals, it can also take into account the rollups. So note that our 10-second series has a 1-minute rollup. When you're defining your different schemas, well, first of all, the more you keep your different series on the same schema rule, the simpler everything gets, of course. But if you want different precisions or different retentions for different metrics, it still makes sense to make them correspond to one another. Perhaps our second metric would be just as fine as a 1-minute series instead of a 30-second series. If we change it to a raw interval of 1 minute, it would match the interval of the first rollup of our 10-second series. I have prepared another fake series, MyApp2, and this one has a native interval of 1 minute instead of 30 seconds. So now our sum is taking our 10-second series and the minutely series. The result is, of course, a minutely series. So let's isolate the sum metric again, and let's go look at the metadata to see what happened. As we can see, now Metrictank could pre-normalize. During the planning of the query, before query execution, it knew that we were combining our series with a minutely series. So for our 10-second series, instead of fetching raw data and consolidating at runtime, which is expensive, it planned the query to simply pick the 1-minute rollup instead, which is equivalent to doing normalization. I mean, it results in the same data, but it's much more efficient because there's less data to load and to process. Note also that it correctly used the sum rollup because we have asked for it using the consolidate by call. Now, let's go back to the stats. We can see we only fetched 30 points instead of 120. That's a 4x reduction. Now, of course, our data is only half as precise as before, but even taking that into account, we still had to fetch much less data. This is a trivial example, of course, but it's helpful to keep this in mind. If you are matching series with different intervals in your queries, you may be able to achieve higher performance by matching raw resolutions of one series to the rollup resolution of the other. So we have arrived now at the last section of this presentation, which is some updates around the Metrictank open source project. At Grafana Labs, we feel that it's important for Metrictank to grow into a little bit more of an independent open source project and have a more broad and diverse group of people setting the roadmap. And we wanted to make sure that the way the project is governed is clear and transparent. So we have established a governance. You can read the document in our docs if you want. The current set of team members is not a big surprise probably. It's basically the Grafana Labs Metrictank team, as well as Sean Hansen from Bloomberg, who is a terrific contributor. And we are looking for more people to contribute to the project and eventually maybe also become team members who get a seat on the governance. So where can you find us? Well, you can find us on the Grafana Slack. There's a Metrictank channel. Of course, for this presentation, questions will go to GrafanaCONline, but in general, if you want to know more later about the Metrictank project specifically, feel free to join the Metrictank channel as well. We have monthly calls for the community. We publish the agenda in advance, so if you're interested, feel free to join. And to conclude, the takeaways of this presentation are meta tags. They're really useful in enriching your metrics. So they add a lot more information to your metrics so you can understand better what's going on. You have more dimensions to aggregate or segregate your data by, which can be really helpful when troubleshooting incidents, as we saw in the example earlier. There's performance metadata, which helps you understand why your queries are slow and helps you optimize your queries. There's lineage metadata, which tells you whether your data came from raw data or from rollups, whether it was runtime consolidated, and so on, which helps you understand what's happening with your query and also make sure that your query does what it should be so that you don't run into mistakes. And also you can use the metadata to improve on the normalization, as we saw earlier, by taking advantage of Metrictank's pre-normalization. Finally, we also went over some updates from the open source projects. I hope you found some interesting updates in there as well. So thanks from myself and the Grafana Cloud Graphite team at Grafana Labs. We are all available on GrafanaCONline to answer any questions you may have.